should do instead is make sure that you're comfortable with this logic, that you use named elements to make it easy to understand what they are, or easier to understand what they are, and then work with that single assignment. Finally, is a string in use? Pass in the name, pass in the string. And again, I'm going to be using the exists method to ask, does an element exist at that location? So first, does the list exist? Because if the list itself has not been defined, clearly no string is in use in that list. So if the list exists, then go to that list name in the list. This whole thing is, once again, a record. That record has as one of its field the list of values. This is a collection. And the question is, have I already used this string in this list of values? So I ask for exists on that string, and it returns true or false. And that's it. Now, if you want to, an alternative approach is I could have a single return statement, which you see here. And I say simply, go to this list, within this list of lists, and ask, does the element exist at that location? So a single return statement instead of all that other code. And what I'm going to do here is assume that the list name exists. If it doesn't exist, Oracle will raise the no data found exception, and I return false. You could certainly take this approach. The only reason that you might object to it is that we're essentially using the exception section as a kind of conditional branch. And it's not really a best practice to do that. So instead of burying that kind of logic inside the exception section, I keep it all in my executable section and simply ask first, does the element exist? If not, well, obviously, the string's not in use. Otherwise, use the exists for my lower level collection. The thing to remember here is that the exists method can only apply to that collection it's attached to. It can't also go up through your multi-level collections and ask, does this also exist in this collection? It doesn't work that way. So you have to ask it at multiple levels. One other little point in terms of the extension of this package is the idea of backward compatibility. And in fact, I need to finish what I was doing for backward compatibility. Let's just take a moment to copy in some code and explain to you what I'm talking about, because somehow I lost the part of this code from my package specification. So what I'm doing is adding back into my package specification 3 programs that support the original API. So remember, this is my first string tracker package. Mark is used, string in use, and there was no idea of a named list. It was just a single list. I went back to this existing package and I extended it. I added much more functionality, especially specifying the list name for the value string. The problem is that when I made this change, all the existing code that used a string tracker would have been invalidated. Well, that's no good. So what I'm also going to do is add some backward compatibility and then implement those simpler programs with an implicit list name that is declared as a constant in my package. In fact, it's declared as a non-printing character, so it's unlikely anybody would ever use it. The point here is that as you extend your packages, as you add more functionality, you always need to pay attention to backward compatibility as well. Okay, so that's a fairly complex structure. A multi-level collection, a list of records indexed by a string. Each record has within it a collection. That collection itself is indexed by string. Again, I urge you to stop the video, open up these files from your demo zip, play around with them yourself, make sure you understand how they're defined and how they work, and then you're ready to move on. Let's take a look at what's involved in emulating multidimensional arrays. Now, collections in Oracle are always single dimensional. There's no way around that. You can't declare a 3-dimensional array in PL SQL. But a collection of collections, a multi-level collection, is kind of like a 2-dimensional array. It's not really the same, but it's kind of like it. And you can extrapolate from there. A 3-dimensional collection is a collection of collections of collections. And in fact, that's the example I'll show you, how you can define the emulation of a 3-dimensional collection. Here's the basic idea inside the declaration section. I need to declare a 3-dimensional array of strings. So my first dimension is a table of, list of, strings indexed by integer. My second dimension is a table of the first dimension. My third dimension is a table of the second dimension. It's really not the same thing as a true three-dimensional array, but it's the best you can do in PL/SQL. Let's take a closer look. This package was originally written by one of my co-authors, John Bereznovich, who's now a member of Oracle on the OEM team. So I give him all the credit. Now, when working with a three-dimensional array in a 3GL language, like Fortran or C or whichever, you can specify an array as having a certain size, 3 by 5 by 100. It's a single declaration. And then you can reference it in a fairly natural way. So the typical syntax for referencing a three-dimensional array would be the array A, comma B, comma C, X, comma Y, comma Z. That's the typical syntax. That's not how it works in PL/SQL. In PL/SQL, again, I declare a multi-level collection. For every dimension, I need a collection level. So the third dimension is a collection of the second dimension, the second dimension a collection of the third dimension, the first dimension a list of strings. Anything defined of the dim3 type is sort of like a three-dimensional array. So what John did in addition to declaring this complex structure is also declare get and set programs. To set a cell value, I pass in my array my three dimensions and the value that I want to put in that X, comma Y, comma Z location. To get a cell value, I pass in my array and I specify my three dimensions and it returns the value. Let's take a look. Again, typical syntax, if I pass in my X, comma Y, comma Z, would simply to specify the first dimension, comma second, comma third, gets the value. That's the way you can do it in many other languages, not in PL/SQL. In PL/SQL, I would have to do something like this. Okay, array n, that's a dimension array of dimension 3, type 3. So that means that if I use the third dimension right here, this itself is a collection, since dim3 is a collection of collections. So that's a collection of collections. This is a collection. I go to that location in this collection, and this entire thing is a collection. I go to that location in this collection, and that is a string, so I assign the value to it. In the reverse order, I go to that location to get the cell value. I go to my array. I go to its third dimension. This is a collection. I go to the second dimension. This is a collection. I go to the third and last dimension, and this returns a string in the array. This is not very intuitive. Essentially, you're glomming together just index values. Notice there's no dots because there are no named elements. If you have a collection of records or a collection of object types, you have a named element, like list of values. So then I can specify x dot list of values, collection dot list of values. When I simply have directly nested collections like this one, defined by this type, then the dots go away and I simply put together, concatenate together my references to my indexes. This is complicated not only because the syntax is unusual, but you have to remember the right order. For example, is it 3, 3, 2, 1 or 1, 2, 3? Which is why it's especially important when you build structures like this to hide the underlying complexity behind get and set programs, so the individual developer does not have to remember which order to supply things in. They just provide them by parameter name. So that's the emulation of a multi-dimensional array. Again, I urge you to stop your video, play around with the multdim package, try to create elements with it. In fact, if you look at the multdim test script, you'll find examples of using the set cell and get cell programs to set the values. So try it out, make sure it makes sense to you, and then proceed from there. Because proceeding from there is the last example, and it's the most complicated of all. And it involves a 4-level nested collection. And it's definitely the most complicated structure I ever built. And I used it to build a utility to analyze packages for potentially ambiguous overloading. Now what I'm going to do with this example is explore the implementation. I'm going to explain why I did it, how I did it at a high level, focusing on the multi-level collections and giving you a sense of the thought process I went through to get to my final implementation. It's way too complicated to try to explain fully in this lesson, and it would be much too long. Instead, what I did was write a 90-page series of articles, an 8-part article series that I published on OTN that explains this in great detail. Not only the nested collection side of things, but also the modularization that I needed to do in order to be able to understand what I wrote and explain it to others. To see this 8-part article series, visit stephenfeuerstein.com/read-Stephen, or just go to stephenfeuerstein.com and click on the Read Stephen. Here we go. Click on the Read Stephen page and you'll see the link to the series there. So again, the idea over the next several pages is not for you to fully understand all the aspects of this implementation, just to get a sense of the kind of thought process you might go through as you start working with your own complex scenarios. And to reinforce the point I made at the beginning of this lesson, multi-level collections really do stand in as a kind of normalized database design. And in fact, that was specifically what I ran into in this particular example. And I found that coming up with the right model of multi-level collections, is it a 3-level collection, is it a 2-level collection, 14-level collection, is similar to normalizing data in relational tables. In other words, you want to go for the same objectives. I want to avoid redundancy. I want to accurately reflect the relationships between my data. And I want to simplify, that should be simplify the resulting application code. So let's take a look at an example. So first of all, the problem of ambiguous overloading. Strangely enough, it's actually possible to compile an overloading in a package that is not usable. Here's a package. The sales package has 2 programs called calc total. They each have a single parameter with the same name, and their data type is different, varchar2 versus car. Now, unfortunately, that's a difference, enough of a difference, the varchar2 versus car, to allow Oracle to compile this package without errors, which I think is a really bad idea because it turns out there is no way to actually call the program. Any way that I try to call the program will result in an ambiguous overloading, which means that Oracle can't figure out what to do. I'll open up that file. And you can run this yourself to take a look at the problems with ambiguous overloading. But the bottom line is that when I try to use these programs, I get messages like this. Too many declarations of calc total match this call. That's an example of ambiguous overloading. So if you're not careful, you can put these kinds of ambiguities into your code. Usually the ambiguity is not as extreme as this. You can't even use this package, not at all. No ability to use that package. Often it's more subtle depending on the fact that you have multiple parameters with default values, and if you leave off the default values, your overloading might become ambiguous. So anyway, I decided that this is a big problem and I want to help you. And I decided to build a utility that would automatically scan your package specification and identify ambiguous overloadings or the potential for them. Now, how can I do this? Well, one of the things I could do is write a parser of your PL/SQL code, parse this package, get out all the information about those programs and their parameters, and do my analysis. Well, I'm not a trained computer scientist. I'm a self-taught programmer. So building a parser for PL/SQL is way too complicated. And what I did instead was look around inside the Oracle Data Dictionary to see, is there a view that would help me get this information? And it turns out there is. It's called All Arguments. And All Arguments is a data dictionary view that contains information about all the arguments of all the procedures and functions to which I have access. Well, it seems like I should be able to use the All Arguments data to do my analysis of ambiguous overloadings, because it has all to do with the arguments, the parameter list. Now again, I'm going to be showing you lots of links to files. I'm not going to be showing you and running all these files. I encourage you to do so on your own to learn in more detail how I had to work with all arguments and some of the challenges I ran into. And as I found, what is very common with a lot of the data dictionary views is that Oracle offers us a whole lot of pleasure mixed with some pain. In other words, a whole lot of really good data, but often not very well organized. And in fact, All Arguments is one of the worst defined data dictionary views I've ever seen. It's kind of bizarre in terms of how they structured it. It's very much denormalized, and it's incomplete. So I even had to complement my use of All Arguments with the dbms describe package. Like I say, Way too complicated to get into in this lesson. Let's just focus on the data structures and how I got to a 4-level nested collection. So I decided that I needed to use the all arguments data dictionary view, grab the data from the view, drop it into a collection, and then work through the collection, the contents of the collection. So what I did was the same old, the first inclination, the first reflex, which is to grab all the data from all arguments and dump it into a collection based on that view. That certainly is easy enough to do. So I declare an associative array, which is a table of rows from the all arguments view that emulates the array structure. And then I can populate that array structure by querying all the data from all arguments for a given package and dropping it into my collection of records. So this was really easy to do. It's a very powerful aspect of working with collections and collections of records. So I did that. And then I needed to start writing code. And what I found myself doing was writing lots and lots of really cumbersome, awkward, complicated code. For example, the all arguments data dictionary view, like I said, has denormalized data in it. So it has all the arguments for all the programs in all my packages in one view. Well, I need to pull out all the arguments for a given program. So what I found myself doing was writing loops through my big array and asking, well, if the current object is not the same as my last object name, then my program name is changed. Therefore, I need to start up a new analysis. And even within that list of programs, even within a program of that name, I had to worry about the overloading. I might have multiple programs with the same name. That, in fact, is the scenario I'm looking for, ambiguous overloadings. And I needed to find out, well, is my overload number different? And if so, then I'm starting with a new overloading, so I do new stuff instead of the same stuff. The bottom line, without trying to explain all the details here, is that I got seriously alarmed by the complexity of code I was writing. And I stopped myself and I said, Stephen, if you're going to build this utility, you've got to figure out a better way. There's something wrong here. You made a left turn when you should have made a right turn somewhere along the way. So that's what I did. I took a step back and I realized that the problem is that the all arguments data dictionary view is one view, but it has multiple levels of information. Each program has one or more, 0 or more overloading. So a program might not be overloaded, or it might have multiple programs with the same name. Each overloading has n arguments. One of my overloadings has 2 parameters, another has 3 parameters. Each argument itself can even have multiple levels of all argument data, because if my parameter is not scalar, if it's a record or an object type, then all arguments data dictionary view actually contains information about each individual field or attribute within that argument. Here's what it came down to. I have multiple programs. Each program can have multiple overloadings. Each overloading has multiple arguments, and each argument can have multiple breakouts. That's the actual structure of the all arguments data dictionary view. It's not a single view. In fact, it should be like 4 different views. Okay, so what do I do with that? I went back to my definition in my package, and instead of having a single collection of records, instead I created a 4-level nested collection to mimic the structure that I saw right here. Let's start from the bottom. First of all, my programs are organized by name. So I have a collection, an associative array indexed by the object name, the program name. And it's a list of overloadings of that program. Each overloading has an overload number, so it's indexed by integer. And it's a table of the arguments for that overloading. Each argument or parameter has a position in the list, so it's indexed by integer. And that has a table of breakouts. The breakouts are the actual rows in the all arguments table. For a scalar parameter, it's a one-to-one relationship. There's one breakout per argument. But for non-scalars, I might have multiple rows of information for a single argument. So there's my 4-level nested collection. And once I made this change to my 4-level nested collection, I found that it was, first of all, really easy to populate this complex collection. It looks like it would be really difficult, but it wasn't at all. So originally what I did was assign my record to my single level collection of records. That was certainly easy enough, and I added it sequentially to the list. But now what I'm going to do is take that same record and I'm going to add it to my 4-level nested collection. So I use my record object name to specify the name of the object. My record overload is my overload number. The position is the position within the list, and the data level is my breakout level. So with this single assignment, it automatically populated across 4 levels of my nested collection. I didn't have to write a loop, loop within loop within loop. It basically did it all for me automatically, and essentially did a select distinct on program names that have results. So it automatically distributed the data out across all 4 levels of nested collections. It's a really, really nice, powerful statement that hides a lot of work. So there it is. One assignment populated my 4-level nested collection. Oh, and just a little comment here before I go on. The CC SmartArgs is the package body that I built as a part of this big utility that does this kind of operation, does the assignment. It's, of course, a bit more complicated than this. And you can take a look at the load arguments procedure to get a sense of the more complexity, the higher level of complexity involved. But at its core, what I'm doing is that single assignment that spreads across my 4-level nested collection. And what was really wonderful about it is that once I went through the process of creating my 4-level nested collection, which was quite complicated, and I didn't get it right the first, second, or third time, and then once I wrote the code to populate the collection, getting information out or querying the contents of my collection was very, very simple. For example, is the top sales program overloaded? Well, go to the top sales location in my list of program names and find out how many overloadings I've got. So L programs is a 4-level nested collection. This particular named program brings me down to my second level of nesting. These are all the overloadings for this program. If I have more than one, my program is overloaded. Is the second overloading of top sales a function? Well, go to all the overloadings of top sales, go to the second overloading of top sales, and find out if I have an argument, a position, an argument at position 0. And in the parlance of all arguments, that means that it's a return, not the first argument or second argument. If there's something at position 0, that means it's a return statement, which means it must be a function. What is the data type of the return clause of the second overloading of top sales? Go to the top sales location in my list of program names, go to the second overloading, go to the return clause, that's location 0, and then get the data type at that level. Now, I'm not expecting you to understand these magic values in all arguments. That was part of the problem with me learning how to work with all arguments. Don't worry about that. The point is that instead of writing lots and lots of code, iterating through multiple levels of nesting, I can answer a complicated question with a very simple, trivial piece of code once you sort out the magic values and the parsing of this kind of logic. And now it's all taken care of for me because all the intelligence is built into the data structure itself. Now, again, the point of these slides is not to have you fully understand the utility I wrote to check for overloading. It's a lot of code. Like I say, it took me 90 pages just to explain how I did it. What I wanted to show you in these slides is how you can move from a very complicated world in which you're writing tons and tons of code because the underlying data structure choice was wrong, and instead say to yourself, wow, no, that's not good, I don't want to go there. Reevaluate how you've constructed your data structures. Come up with a normalized approach inside multi-level collections, and then find that the resulting code is much simpler than it would have been. Draw some conclusions. The multi-level collection is a powerful but obviously very complicated feature. The more levels of nesting, the bigger the headache you will have trying to understand how to do the nesting and then write the code for it. But used correctly, it can hide complexity in the underlying data structures and simplify your algorithms, your code. So get the database design right. That can be complicated, but also usually fairly straightforward, certainly if you're used to normalizing database tables. And then the resulting code is much, much simpler to write and certainly simpler to maintain. So again, if you find yourself saying it shouldn't be this hard, you're almost certainly right. It shouldn't be that hard. It's not that the challenges that you have to tackle aren't hard. Business requirements can be very complicated. But it doesn't mean that the code that you write should be that complicated. And multi-level collections could be a great way to help you simplify your code. Next steps. Download the demo zip if you have not already done so from PL SQL Obsession. Run the sample code yourself to reinforce the lessons. I say this at the end of every one of my lessons, but for this one, I really, really mean it. Use the different files I give you. Go through each of these examples. Make sure you understand it. Start with the simplest ones. Work your way up. And if you can make your way through all these examples and the sample files and actually understand what's going on, you're going to be in great shape to build your own multi-level nested collections. And of course, explore the other advanced topics for collections. Working with non-sequential indexing, that's critical for this one actually. Using string index associative arrays, again, very important to know before you take this lesson, but take it after as well. And set level manipulation of nested tables using the multi-set operators and other really nice set level features of nested tables. Well, I hope this was of use to you. I find multi-level collections to be one of the most complicated but also exciting and challenging aspects of PL/SQL. I hope you tackle the topic, master it, and put it to use in your PL/SQL based applications. Happy PL/SQL coding.